Let's consider the present value of an ordinary annuity. This formula can be derived in a fashion similar to the one for future value. I will not do that here, but we're going to use it. It looks similar to the future value of an annuity formula. Notice my I is still R over M, rate per period. N is still the number of payments, which must match the number of compounding periods. Okay, remember this is an ordinary annuity. Ordinary means that the payments are at the end of each compounding period. And our present value represents the present, our PV represents the present value of all the payments. Let's use this in an example. How much should we deposit into an account that pays 6% compounded semi-annually so that $1,000 may be withdrawn every 6 months for 3 years? You might do something similar to this. If you are trying to deposit a large lump sum, you had some money, but you want to be able to allow a child or perhaps an aging parent to make periodic withdrawals for a certain amount of years. This would tell you how much you should deposit at the beginning. So here we use our formula. How do we know which formula we're going to use? First, we look for periodic payments. That tells us we use one of the annuity formulas. Then we ask ourselves, is the large lump sum occurring at the beginning, before interest, or at the end, after interest? Here we are depositing the large lump sum at the beginning, so we use the present value formula, not the future value. You need to not only be able to use the formulas, but also to decide which one to use. Okay, let's put in all of our information. We know that my I is equal to R over M, so this will be 0.06 divided by the number of compounding periods, which would be 2 per year. My N is equal to the number of compounding periods per year times the number of years, so that is 2 per year times 3 years, so 6. My payment is $1,000. So we have $1,000 times 1 minus 1 plus 0.06 over 2, all raised to the negative 6th power, divided by 0.06 over 2. Again, I suggest working with the most complicated part, which would be the numerator of this expression in brackets. Divide by that denominator and then multiply your answer by 1,000. Do it along with me and make sure that you end up with 5,417.19. So, ask yourself, does this answer seem reasonable? Well, how much will we withdraw total? We'll have 6 payments of $1,000. And so it makes sense that since our money will be earning interest, the initial investment should be a little bit smaller than $6,000. And it is, so I would say this answer seems reasonable. This can also be used for amortizing or paying off a debt. We call that amortization of a debt. Okay. Think of a debt. Borrowing is exactly the same as the first scenario, except from a different perspective. From the lender's perspective, what they are doing is they are paying out a lump sum now in order to be assured of equal monthly payments later, just like we did in that first example. So here, let's suppose that Scott decides to buy a fancy flat screen television for $800. He plans to make equal monthly payments for 18 months at 18% compounded monthly. We want to find out what his monthly payments are and also how much interest he will pay. We know that my M is 12 and my R is 0.18, and therefore my I, R over M, will be 0.18 divided by 12. How many payments will we have? Equal monthly payments for 18 months. That means we will have 18 of them. We notice that we are making periodic payments. That means we have one of the annuity formulas. Do we use present value annuity or future value of an annuity formula? Well, where is the big lump sum occurring? What's the big lump sum? This $800. Is it occurring at the beginning or the end? At the beginning. That means we're going to use the present value formula, and that our present value will be $800. Okay, let's put everything in. So here we have 1 minus 1 plus 0.18 over 12. Again, make sure you don't round until the very end. Okay, again, I would suggest that you simplify this complicated expression in brackets first, starting with the numerator, divide by the denominator, hit enter, whatever on your calculator, and you should get a number for that part in brackets. Then take $800, divide by that number. Make sure you do not repunch that number. Either use the answer or the memory recall on your calculator or store it somewhere. You do not want to round until the end. You should end up with a payment of $51.04. Make sure you ask yourself if that seems reasonable. I believe it does. Let's figure out how much interest he paid. Remember, interest is the cost of borrowing money. Everything that was not paid in a payment is interest. Okay, so what we want to do is we want to figure out the total of his payments so that'll be 18 times 51.04. So that would be $918.72. So then my interest is equal to the total of the payments minus the initial cost of the television. Maybe instead of saying cost of the television, I should say price, because that was what was on the price tag. You'll see it really ended up costing $918.72 if you factor in interest. But the initial price was $800. In other words, that is the present value. So we end up taking our $918.72 minus the $800, which was the actual price, and so that gives me $118.72 in interest. That's how much interest was paid. Let's do another one. Let's suppose that I buy a car for $15,000. I put $700 down and the dealer will give me $800 for my trade-in. I will finance the rest at 5.5% for 5 years, compounded monthly. And this is typical, exactly how a car payment would work. You make monthly payments, the interest is compounded monthly. The car dealers often call it simple interest, but this is what it is. It is simple interest each month, but as a group, the total thing is based on compound interest with monthly payments, which puts us at one of the annuity formulas. Which one? Is the large lump sum occurring at the beginning, before interest, or at the end, after interest? It's at the beginning because I must pay the $15,000 for the car now. So that tells me I will be using the present value formula. Okay, let's figure out what our present value is. So that'll be the amount that is financed. What will that be? Well, that will be the price of the car, which is $15,000, minus the $700 down, minus the $800 for my trade-in, which I could really think of as a combined down payment of $1,500. And so that gives me $13,500. That's my present value. My I is equal to R over M, so 0.055 divided by 12. Again, don't round that number until the end. The number of payments, I'm financing this for 5 years, and I'm making 12 payments per year, so 12 times 5, which is 60. Okay, we put all that into our formula. And we now have 13,500 is equal to my payment times 1 minus 1 plus 0.055 over 12, all to the negative 60. Divided by that 0.055 over 12. Calculate the part in brackets, take the reciprocal and multiply by 13,500, and you should end up with payment. My payment should be, and this is approximation, we'll round it to the nearest cent, we should end up with $257.87. Ask yourself, is this a reasonably priced car payment for a $15,000 car? Use your own judgment on that. I think this answer is reasonable. If I come up with a $25,000 payment or even a $2,500 payment on a $15,000 car, that should tip me off that I made a mistake in my arithmetic or my setup, and I would want to go back and look for it. So always ask yourself if your answer seems reasonable. So that is my monthly payment. Now we want to find the interest. So again, calculate the total of your payments. So we have 60 of them. Multiply by 257.87. And you should end up with 15,472.20. If you wanted, you could add your $1,500 down payment to this and then subtract the price of the car, or you could subtract the amount financed. My amount financed was $13,500. So I'll do the total of my payments minus the amount I financed, and I should end up with $1,972.20. So I paid almost $2,000 in interest on this car. Let's consider a house. Let's suppose we have found a $110,000 house and have saved $10,000 for a down payment. What will be the monthly payment for a 30-year loan at 5% compounded monthly? And again, how much interest? Okay, so once again, we have our present value equals our payment times 1 minus 1 plus I to the negative n all over I. I won't put in quite as much detail here as I have before because you've seen a few of them. Our present value is, we should write down our present value. We have a $110,000 house, right? And we're going to subtract the $10,000 down payment. And so that will give me a present value of $100,000. So in each case, we are financing $100,000. And this time our N will be, it's compounded monthly, so we have 12 times 30 years. So that means there will be 360 house payments. Don't forget that negative sign on your number of payments. Calculate your payment the same way that we've been doing, and you should end up with about $536.82. And so my interest, my total payments, let's calculate first. My total payments, I have 360 times that 536.82. So that is $193,255.20. And so my interest then, since we financed $100,000, the rest has to be interest. So we have $993,255. I'm going to round it at dollars because that's a pretty big number, and I'm not going to be worried about the 20 cents if I'm paying $93,000 in interest. So that's my interest with that first option. Now let's suppose same interest rate, same compounding, but this time we're doing a 15-year loan. Okay, so here my PV, everything's the same, except in this one, my N is equal to MT, so that'll be 12 times 15, or 180, or in other words, only half of the 360 payments I had before. So I put it into the same formula. And you should end up with a payment of $790.79. So a little over $200 more. Let's calculate the interest on this 15-year mortgage. Okay, we would do the 180. Let's write the payments first. In other words, the total money that we spent in payments, 180 times that 790 79 is $142,342 and 20 cents. And so my interest then is the $42,000. Okay, so that's a big difference. Knocking it to 15 years instead of 30 saved them about $50,000 in interest. Let's just do part C real quick. I'll leave most of this for you to do on your own. Here, the only difference is that my I is equal to R over M. This time, we got a 4.6% interest rate, 0.046 divided by 12. Let me check those numbers. Yes, 4.6%, 15-year loan. Okay, and so we still have 180. And what usually happens is if you will make it a shorter loan time, in other words, if you'll go with 15 years instead of 30, you can usually get a slightly better interest rate. But the big savings is in knocking down the number of years. So when we put this into our formula, we should end up with a payment of not a huge improvement, only $20 a month over the 5% interest rate. And it turns out that the interest this way, my interest that I'll get, remember, take the payment, multiply by the number of payments. When you do this, your interest rate will turn out to be, not your interest rate, but your total amount of interest paid will be $38,619.80. And I just did this to show you that the big improvement comes from not changing your interest rate by part of a percentage point, but rather by choosing a 15-year mortgage over a 30-year mortgage. I hope these examples were of use to you in understanding how to calculate present value. Let's just show you one more thing, which is kind of a summary of all these formulas so that we can decide which one to use. First, you ask yourself, is there a single payment or a single lump sum, or are there periodic payments that occur over and over again? If you have periodic payments, that pushes you into one of your two annuity formulas. Ask yourself, is the large lump sum I'm concerned with, is it occurring at the beginning, before the interest is accumulated, or at the end, after the interest is accumulated? If after, you use future value formula. If it's before, you use the present value. If you don't have any periodic payments going on, then you've either got simple interest or you have compound interest. In other words, ask yourself if your money is being compounded periodically. Hopefully this helps you to understand compound interest. Good luck, and I will see you next time.